Look at this piece of curved glass. It takes chaotic, scattered light and perfectly organizes it into a single, sharp focal point. Tracking a single ray of light through this glass reveals a process more complex than a single bend. A lens is a compound system of two sequential, separate spherical refracting surfaces. Light bends at the front interface, travels through the glass medium, and bends a second time as it exits the back surface. To accurately calculate where an image will form, we cannot look at the whole piece of glass. We must isolate the physics of the first boundary, calculate its effect, and then independently analyze the second. Processing these two surfaces sequentially is the only mathematical way to understand the behavior of all thin lenses. By tracking light through this two-step process, we derive the mathematical laws of the laboratory, the lens maker's formula, and the thin lens equation. Modeling this compound accurately allows us to predict exactly how a lens will manipulate the entire visual world. This diagram shows the first stage of refraction. We start with a real object, labeled O, positioned on the principal axis, directly facing the front spherical boundary of our lens. Rays originate from this object, travel through the air, and strike the curved glass at a specific angle of incidence relative to the surface normal. Because the glass has a higher refractive index than the air, the light slows down and bends toward the normal line, converging toward a theoretical point on the axis labeled I1. This geometry yields our first equation. It links the refractive indices of the air and glass to the physical object distance and the resulting theoretical image distance. However, image 1 never actually forms in physical space. Before those converging rays reach the I1 position, the second curved surface intercepts them. This interception introduces the concept of the virtual object. Even though image 1 does not physically exist, the incoming rays are still targeting it. For the mathematics of the second surface, that theoretical target acts as the source, the virtual object. The lens functions through an optical handoff. It turns the theoretical output of its front face into the literal input for its back face. This is the equation for the second stage. It treats the virtual object as the starting point to calculate the position of the final physical image, I. We currently have two separate equations dependent on an imaginary middle point, measured from two different physical poles on the glass. We resolve this by applying the thin lens approximation. If the physical thickness of the lens is negligible, the distance from the front surface to the virtual object is practically identical to the distance from the back surface. The separate poles merge into a single optical center. With those internal distances equalized, we can algebraically add the two surface equations together. When added, the terms containing the virtual object perfectly cancel each other out. The imaginary midpoint disappears from the algebra. The resulting equation directly links the initial physical object to the final physical image. We apply the standard Cartesian sign convention, assigning u for the object distance and v for the image distance, both measured from the optical center, yielding the thin lens formula, 1 over v minus 1 over u equals 1 over f. The complex reality of light refracting twice inside of solid glass mathematically distills down into this single, powerful equation. The thin lens formula predicts the behavior of light, but the physical properties of the glass determine the focal length itself. To understand the engineering of a lens, we look at the right side of our combined equations. This section holds the statistical parameters, the refractive index, n, and the radii of curvature for both the front and back surfaces, labeled R1 and R2. This arrangement is the lens maker's formula. By precisely grinding the curvature of those two surfaces, engineers permanently set the focal length of the lens. Once that focal length is established, it dictates the linear magnification, or M. This is the ratio of the final image distance to the object distance, determining the size of the image relative to the object. The physical shape of the curved glass strictly dictates the algebra, controlling the exact size, orientation, and position of the image. Because the mathematics of this double refraction are constant and reliable, physicists use visual shortcuts to trace the path of light. We rely on predictable ray diagrams. Rule 1. A ray parallel to the axis refracts through the second focal point. Rule 2. A ray through the optical center emerges without deviation. Rule 3. A ray through the first focal point refracts parallel to the axis. These same geometric rules apply to concave lenses, with the light rays diverging from the focal points rather than converging. Finding where any two of these predictable rays intersect instantly reveals the exact location of the final image. The complex interaction of light refracting twice inside a piece of glass ultimately resolves into three simple, elegant lines.